Mike Radzicki is an economist and simulation scientist at Worcester Polytechnic Institute and director of the WPI Complex Systems Laboratory. His work focuses on developing techniques for applying system dynamics models and games to complex socioeconomic systems. Mike, thank you so much for taking the time today.
Well, thank you so much for having me.
So I'd love to start just by talking about what systems dynamic is, and how we can use it. Can you kind of give us a high level definition?
Sure, that's a question that I'm asked quite often, actually. What is system dynamics? And I usually say, like a lot of questions in economics, it depends, but it depends on who's asking me. 9 out of 10 people, I think, are domain people. They're not tools people. So if you go and give them a big tools explanation, usually they don't want to hear about it. They want to hear about the domain area to which we apply it. But if you're more of a tools person, a mathematically oriented person, system dynamics modeling involves simulating nested nonlinear ordinary differential equations. So for most people, that they float to the ceiling when they hear that. For everyone else, system dynamics is a modeling tool that enables us to redesign the airplane. We have a complex socioeconomic, technical, environmental system that isn't flying or performing very well. And so we want to define first, what do we mean by improved or better? We want our airplane, our socioeconomic airplane, to fly higher, faster, more fuel efficiently, carry more cargo, generate less emissions, be quieter, whatever the laundry list is. And we say, all right, we're not going to just throw the system away. You can't really. What might we reconfigure it, redesign it so it exhibits improved behavior? So that's one sort of average citizen way of thinking about system dynamics. And the other, which I found over the years is very important, is we can use system dynamics to help experts and stakeholders reach a consensus. Not always, but we have a lot of successes there. And actual policymakers, when we work down in Washington, for example, will routinely say, when something bad happens, the president, the governor, the whatever in charge says, get the 10 foremost authorities in the world in here and have them tell me what to do. And they're all exasperated. They get in a room and they can't decide what to do. They give you 5 different explanations. They can't agree. So, getting experts and stakeholders to reach a consensus is also a very valuable sort of average citizen way to think about system dynamics.
So how is this, you described kind of the socioeconomic airplane. Is this different or in addition to traditional economic thinking or economics in general? How is this different from kind of traditional economics?
A lot to unpack there. It is different. System dynamics origin is really electrical engineering and the theory of servo mechanisms or feedback systems. So in a physical realm, this would be something like a thermostat or a cruise control on a car, where you have a target or a goal, the setting on the thermostat, the speed at which you want your car to travel, guidance system on a missile, the target. And if the system deviates from the desired temperature, speed, or what have you, corrective action is motivated. Now, that's in physical systems, but people have goals, right? Biological systems have goals. Your human body on average is set to 98.6 degrees Fahrenheit. If you go out in the cold weather, you shiver. Your body's attempting to raise your temperature to that desired level. And if you go outside in hot weather, you perspire. It's trying to cool yourself off. So all systems, physical, biological, so have goals or these negative feedback loops, these servo mechanisms. At least that's one of the kinds of feedback loops. And it's not that economists have never heard of feedback loops. They have, but they don't think about them in sort of the servo mechanism manner. So that's one difference. At the macro level, let's go macro, micro. You can divide the world of economics into sort of 2 camps, macro and micro. At the macro level, system dynamics is good at redesigning the airplane, controlling it. If it's bouncing around while you're trying to drink your coffee, how do you stabilize it? If we have a business cycle, how do you stabilize it? But with the advent of rational expectations, macroeconomics in the 70s forward, I think that orientation, I think that's what Keynes originally said, the father of macroeconomics, using the government to stabilize an unstable system, a capitalist system. But with rational expectations, the orientation, I think, was changed to a chess game between the public sector and the private sector, between government officials and private citizens and businesses, and they're trying to outwit one another in a chess game. I know that you know that I know that you know kind of stuff. And it got away from this sort of control idea or stabilization idea. So that's one reason, a sort of a traditional macroeconomist might not like system dynamics. At the more micro level, economists have traditionally thought about economic laws that hold at all places and all times. The law of demand has to hold in 1705, 1805, 1905, and 2025. It has to hold in the US and China and Russia and pick your, so time and place shouldn't matter. It's like trying to be a physicist in social systems. So you want simple models devoid of institutional detail, right? And you take a top-down approach. You start with theory. It has to be logically correct. This is traditional economics. And then at the end, you derive a testable hypothesis. And then you look at the real world. System dynamics is just the opposite. It's inductive logic, not deductive logic. You do a case study at the beginning. The institutional details matter. It's a computerized case study, if you will, kind of like the Harvard Business School's approach, but we make it mathematical and we find patterns and whatever. Also, our models, again, micro level, tend not to have unique and stable equilibria, which traditionally trained microeconomists like to see. So there's just a lot of reasons in terms of the sort of the philosophy of science or how you do science properly, where traditionally trained economists aren't going to like system dynamics because they just don't think it's the way to properly do economics. We could go on, but that's kind of the gist of it. There's just a disconnect between the proper way to do economic science.
So you mentioned that economics kind of traditional economics is concerned with unique and stable equilibrium. Is it accurate to say that system dynamics is a more accurate depiction of the real world because there are just so many more, like so many things happening dynamically that traditional economics can't capture or doesn't capture?
Well, I think so. We could build models that exactly replicate traditional economics results that have a single, unique, stable equilibrium or whatever. But our models can do more things, and usually that's where the interesting things happen. By the way, within the realm of traditional micro, you have what's known as Homo economicus, or rational economic man, where the assumed agents are like Mr. Spock. They're human computers that solve constrained optimization problems in their heads. They maximize profits, they minimize costs, they maximize utility or satisfaction. And when you say, well, people can't really do that, psychologists and behavioral economists will tell you that. They say, well, we know that, but these are models, they're not real. So don't criticize my not real model by saying it has a not real assumption. Moreover, they think they predict well, not what an individual household member or an individual manager will do, but what households and firms at the micro level will do. So again, they have a machinery that in their minds works well, and it's just different from how things are done in system dynamics. Yeah, system dynamics, you map out more what a manager would be looking at if you're building a model of a company, for example.
Well, so how can we use system dynamics to help us understand our world? You mentioned the kind of the socioeconomic airplane, and also how we might pursue a sustainable future and solve societal problems.
Big picture.
Yeah.
Well, good question. So first of all, sustainability. So that's kind of a big area in system dynamics. Traditionally, the guy who founded our field, Jay Forrester, one of my mentors, famously wrote a book called World Dynamics, came out in 1970, where he, working with the Club of Rome, produced the world's first sort of socioeconomic world systems model. And it became a very well known, the book was an international bestseller. the Club of Rome said, you were one guy who modeled the world. Maybe we want to redo this thing with a team of experts because you're getting so much attention, which they were happy about, but they were a little bit, And he said, well, I'm busy with doing other stuff, but I'll have one of my former doctoral students do that work. So Dennis Meadows assembled a team. They redid the study. They created a bigger model and what have you. And they published that in a book called The Limits to Growth, which became an even bigger international bestseller. That came out like a year later, I think 71. And this is really sustainable economic development, right? Way before the Rio Summit and 92, the Earth Summit, Rio de Janeiro. And, today sustainability is a commonly used term, but it wasn't back in, 1970 when Jay was originally doing this work. So it's one of our foundational things in system dynamics. If you want to sort of boil it down, what does that mean? Sustainability to a system dynamicist anyway. I'll also integrate it with economics. It's supply and demand. You have the demands on a system. In the original modeling, it was a growing population that was demanding ever more things, right? As well as more food, more water, and what have you, therefore needing more natural resources, therefore needing more agricultural land and what have you. But unless you can overcome the laws of thermodynamics, you're also needing to generate more pollution as you create more things for people, right? And that's the demand side. So the supply side is the carrying capacity of the system. And at some point, if the demand exceeds the supply, if the demands on the carrying capacity exceed the supply side or the carrying capacity, you can wreck the carrying capacity. You can overwhelm the natural environment's ability to naturally absorb pollutants, for example. You can harvest so many trees that the seeding and planting can't catch up, et cetera, and the system can collapse. So sustainability is like, well, how do you balance the demands on the carrying capacity with the ability of the carrying capacity to meet those demands? And it's tricky business. And one last point about the sustainability, the demands are growing exponentially. Real systems that are living don't grow linearly. Everybody thinks they do, but they don't. They grow exponentially. Even if they're growing exponentially, you look at the data for certain chunks of the data, it looks linear on the scale of the graph and what have you, but it's not. And exponential growth is both insidious and powerful. It sneaks up on you, and before you know it, boom, it goes through the ceiling. This is why cancer, they say, catch it early or we can't help you. One cell goes to 2 to 4 to 8, they can do something. But if you let it get out of hand, they can't stop it. So the demand, it's tricky. When demand is growing exponentially, managing the carrying capacity is tricky. And you either expand the carrying capacity with technology, or you back off on the demands with getting people to live a different lifestyle.
So I want to talk about your simulators, and so in terms of thinking about sustainability and understanding what the future might look like. Can you tell us about your simulators and the work you're doing with games and how they work and what they're used for?
Yeah, sure. Well, so one of the things that we found over the decades really of doing system dynamics modeling is that the models are very insightful to the people who build them, either an individual sitting in their cubicle or where you're working with a group of experts and stakeholders. The modeler might know a lot about modeling, but not that much about the domain area. So they need the sort of the mental models of experts and stakeholders to tell you how things work. And if you work with the experts and stakeholders, the domain experts, it becomes their model. They're telling you what they know, and you're putting it into the model. And it's insightful for all those folks. But then when you want other people to benefit from the model, people who didn't help to create it, it gets to be quite difficult. So how do you pass on the insights from this sort of modeling to others so that they, let's say, change their behavior or begin to have educated conversations about whether it's climate change or government financing or, whatever the world's grand challenges and wicked problems and all that stuff is, how do you do that? And we found that turning models into user-friendly games, not haha, let's kill zombie games, but serious games that are accessible to people and they're engaging. They might actually be fun too. is a powerful way to pass on the insights from a model. Instead of saying, here's the 10 insights, I'm going to write them on the board, please copy them down, memorize them, and what have you. No, that's not fun. People discover the insights by playing the game. And actually, it usually takes multiple plays of the game. So it really becomes a flight simulator. You begin training like a pilot trains in a simulator to fly, quotation fingers, the socio-technical, economic, environmental system. And of course, if you're in the simulator with a simulated, pick something 747 or what have you, and the instructor throws a wind shear at you and you do something incorrect, you push forward on the yoke when you should have pulled back or whatever, I'm not a pilot, but and you crash the simulated 747, you haven't really crashed a real 747, right? The instructor says, okay, what do we do here? We threw this at you and you reacted incorrectly. Let me make some suggestions. Let's play again. And they might not throw the exact scenario at you, but you're learning how to fly, the dynamics of motion of that aircraft. So in our case, we're trying to get people to understand the dynamics of particular socioeconomic systems. And you got to be careful. If you make, modeling the world, as Forrester did, let's run the world, that gets a little bit heroic. But properly done, the games can be very powerful at letting people discover insights about the dynamics of complex systems.
So in the context of our economy and sustainability, and you kind of described trying to achieve like a homeostasis in like biological and physical systems. Can you use these simulators to test out different economic policies or agendas and see how much like the emissions in the economy change, how it affects people across socioeconomic status, and how like the national debt is affected? Could you are these simulators capable of doing all those different things at the same time?
Sure, 100%. Now, remember, models are simplifications of reality. So you don't want to try and build the mother of all models that it can answer all questions. Trying to build a digital twin of the world, right? That's ridiculous. Some people kind of try and do that, I guess, but that's not a good idea. What we do is we don't model systems, we model problems from a systems perspective. So we start with a statement. What's the issue, the problem, the curiosity, the thing you don't understand, the grand challenge, whatever the case may be. And let's talk about the stuff that's important to that question. And let's put that into our model. We actually make a picture of the problem statement, a dynamic picture called a reference mode. And we want the base run of the model to mimic those problematic dynamics. So it's mimicking the picture of the problem, the dynamic picture of the problem. Then we have an explanation for the problem. And now we can start to run what-if experiments to see if we can change the dynamics to a preferred flight path for the socioeconomic plane. And it's fun to test what's in the news media or what a politician is saying. So-and-so says we should do this. Okay, let's try that on the model. Now, what you find is a number of interesting things. First of all, better before worse behavior or worse before better behavior. So often what is intuitively obvious does get you the right results in the short run. You shove the system the way you want it to go, and guess what? It goes that way. But then these negative loops hold the system back to where it wants to be. Excuse me. So you can shove the system by pushing the person into the steam room, and but they will start to perspire and try to resist that heat, right? So because of these negatives, these servos, very often the goals of the policymaker are not aligned with the goals of the population. So when you have a tug of war between, it's like two thermostat or a husband and wife, they got an electric blanket and they're both trying to control the temperature in the bed. They have different goals. One likes it hot, one's likes it cold, or the firmness of the mattresses, whatever, right? So you get into policy resistance. So very often these systems are resistant to policy changes, or you get what you want in the short run, but in the long run, it goes back to where it was, even worse than it was. Or it gets worse in the short run, but then it adapts and gets better in the long run. The problem there, of course, is policymakers live on short run timeframes, quarterly earnings, 2-year cycle for the House, 4 for the president, and so forth, right? So short-term thinking tends to overcome the long run, ideas. So what you want to do, sorry for sort of being long-winded here, but what you want to do then is use the models when you're testing various policies advocated by others, or some that you come up with on your own through playing with the simulator. You want to look for leverage points. So you can beat on these systems all over the place and they just resist and pull back. But every once in a while, you find a place where a little bit of effort gets you a big change in behavior. And that's, you can use the models, the simulators, to look for leverage points. And then to see, okay, if we intervene here, we get a big, now we don't want to intervene incorrectly and get a big bad result. Now you have to think, well, how do we redesign the airplane at this leverage point so as to get a better result?
So with the simulators, can you, I think what you just described was having, so I guess in my mind, when I think of like a flight simulator, there's a pilot and they're testing out the simulator. But I think one of the ideas you just described is that you can run different scenarios such that you're thinking about different types of pilots. So does that, am I thinking about that right? Where you're able to test different trajectories and kind of understand what happens if you go left versus go right, and find those leverage points that you're talking about.
Sure. Yeah, of course. So different people are going to have different mental models, different understandings when they first get in the simulator, right? And start messing around in an educated, hopefully fashion, not willy-nilly. And so, yeah, you try and guide them at first so they get an understanding of how things work, and then you let them freestyle, let them try things, right? And different folks are going to have different ideas about what's proper and what have you. But what we also find is it's very rare to have a situation in which you have a complex socio-technical, environmental, economic system that's experiencing a problem, and there's one variable that's going up and that's bad, and you intervene here and it goes down and that's good. Hooray, we have the answer. That almost never happens. What happens is the way you define the characteristics of your good city, or whatever the case may be, whatever the system is through a number of attributes. You know, what do you want for a good city? What makes a city a good place to be at? Well, I want low taxes, lots of open space, lots of shopping, low taxes, good schools, no potholes, low crime rate, and whatever. And what you find out is once you get people to define the dozen or whatever the number of characteristics is that they regard as important for the airplane, it's got to fly high, it's got to fly fast, it's got to fly silently, it's got, you find there's trade-offs. So when I intervene here, I get more of this and less of that. If I intervene here, I get more of that and less of this. So then you get into, on net, what do you want? There's always you're managing trade-offs. You're not finding optimal solutions, which again kind of differs from traditional economics. And that gets you into value judgments. Let's say you have a dozen characteristics of your company, your city, your university, your bank, whatever the institution is. Do you weight them all equally? Are they all equally important? Or do I'd like to have opera in my city, but a good school is better. So I give a weight of 10%, 0.1 to good opera, but I give a 0.9 to good schools or whatever. And different people are going to have different values, right? So then you get into, in the simulator, do you want everybody to specify their own values at the beginning? Do you want the computer to record the last 1,000 people who played the simulator and find an average ranking? You could have everything. We don't know the answer, so everything's equally weighted. Then you can compare. You can have it do all those things and just say, let's look at, does it matter, right? What you think versus what everybody in a consensus view thinks versus what everything's rated equally. But there's no truth here. I guess maybe that's what I'm trying to say. These models are very complicated mathematically. There's a whole lot of technical stuff going on. They're just formal opinions. When push comes, we can ask the model to be fit to numerical data, and there's powerful algorithms that'll do it. So the real data does this, and the simulated curve looks very similar to it. All good. But the idea that that's truth is ridiculous. It's just we're taking what we know as an individual, or there's a consensus view of experts and stakeholders, and making it formal and letting the machine mercilessly trace through the implications of that stuff. But humans can't think it through because it's such a bird's nest of stocks and flows and feedback loops and nonlinearities.
Well, so how do you, given all that, how do you translate this work into policy? And I mean, is it setting up policy recommendations such that they're kind of describing all those different scenarios that you described, and maybe it's if-then scenarios, like if you weight it this way, this is what the policy recommendation is. If you weight everything evenly, this is what the policy recommendation is. Is that how does this translate to policy?
To making the world a better place, right? Which is kind of the idea, right? So $64,000 question, right? Is that the guy who invented this, again, Jay Forrester, was by training an engineer, and he was very hands-on. He was not interested in the theory of bridge building. He wanted to build a bridge to safely get people and cars and such across the river. And he didn't really care about the theory of bridge building. So he's very pragmatically oriented. So Jay always emphasized to us the need to put in system redesigns that an actual policymaker could pull off, right? If you say, raise the nation's morale, and wonderful things happen in the well, okay, how do I do that? I don't know. We have a morale parameter. That doesn't really help anybody to so you have to design policies that are specific enough, sort of micro level policies, I guess you might say, so that an actual policymaker understands what's being talked about in the model. It's not some weird parameter that is just there to make something good happen. But yeah, I do that every day. I set that interest rate every day, or whatever the case may be, and that they can actually pull off. But now nobody is going to make big money decisions, certainly national level decisions, because a model says so. So now, again, 64. So you have a model, a game that is insightful. Maybe it's a little bit different from how everybody else thinks. The economics profession isn't going to sign off on it because they think it's some engineering thing or whatever. It's not. It's okay. So the economists are all saying it's not right. And you're trying to get change in the world. How do you do that? So the gaming, one thought is you put the game out to on a server for free to the world, to the media, to high school teachers who are teaching some environmental class, college, maybe non-economics college professors, politicians, just grandpa and grandma who are retired and are concerned about something, right? And let them, it should be user-friendly so they can pull it off, and they vote, and they go to school board meetings and whatever, and maybe from the ground up you can get societal change. But that's the big the big question. How do you, and these, if I may, I'll paraphrase the famous psychologist B.F. Skinner. Famously, he probably said a bunch of famous stuff, but he famously said, and I'm sort of twisting his words around to make it, I like the way I say it better, but if the ancient Greeks were magically transported to the present day, they would understand absolutely nothing about our technology, but they would understand absolutely everything about our socioeconomic environmental problems because they have not been solved in all these thousands of years, right? So these are these grand challenges, wicked problems, and lots of people that are smarter than Radzicki have been working on this stuff, and we still have them, right? So where are the leverage points? How do you get actual societal change, redesigning the societal airplane from a computer model? I mean, I don't know the answer. You give me the axe and I swing at the log, and I take as many chunks out as I can before I retire.
Well, I'd love to ask you about kind of the future of this work, and there was something you mentioned earlier that I'm curious about. You said that it wouldn't make sense to build a digital twin of the world.
Yeah.
Is it because it's just such a massive undertaking? And is that something that maybe we could task AI with with utilizing system dynamics?
Oh, AI, yeah. So first of all, you say model, have an exact copy of the world. Several comments about that. One is down to what the atomic level.
Mm.
How disaggregated do you get? How far down do you go before it's an exact copy of the real world? I think even with AI today, maybe 100 years from now, who knows? But I don't think it's really possible to do that, depending on your definition of completely, capturing everything. But realistically, why would you want to do that? The idea is I don't understand why we still have poverty, even though we've had a war on poverty at least since 1965, right? So we know how to clean water, yet there's dirty water, causing infant mortality rates to rise all over the world. Well, why is, it's, I don't think it makes sense to try and just model everything, just address a problem and see if you can find leverage points. Now, AI, though, I think is very powerful. Our research group, the Complex Systems Lab at WPI, is, among other things, working on how do you profitably use AI to assist us with this stuff. What you don't want to do, I don't think, is press a go button and Chat GPT or one of these large language models just builds your model for you. Because there's no learning that takes place. It's sort of the struggle to put the model together and understand why the model can mimic the problem. That's kind of where the value comes in. It doesn't come in from the model like it's a work of art at the end that I frame and put a light on it and bow when I walk down my hallway. The model is a means to an end, right? We want to make the world a better place. And the value comes from the learning, from the struggle to understand why, at least from a systems perspective, these things are happening, right? So I don't think, even if we could do it, we don't want to just press a go button and an AI bot or something builds the model for us. But AI can very much assist us humans in building models. A lot of times I was working with a veterinarian who was interested in Lyme disease. And among the things we were modeling is the cycle of ticks and when they get the disease and how it's passed from the host, and and it gets into dogs, and dogs get in the house, and all sorts of stuff is happening in this model. And I said, well, let's pick 1 acre of wooded land. On average, how many ticks are in that wooded area? And what are their average lifespans? I just used Chat GPT and it told me in like 5 seconds. Like, I can use that. I don't have to hunt up or try and estimate it statistically or whatever. Now you got to check it. Like, is it a ridiculous number? And if somebody who does this for a living, I'm an economist, not a whoever studies Lyme disease, a physician or a bug guy or whatever, would look at it and go, that's ridiculous, right? But as long as that kind of thing is a real time saver, or we can use numerical data and say suck it in from a spreadsheet and say, hey, algorithm, fit my simulated model to the actual data. And we can do that. We can talk to experts and they can tell us how things work and we can put that in the model. What about written information? If you're modeling central bank behavior, all the transcripts from Federal Reserve Bank meetings, go read them all. Oh, shoot me. I can get a Chat GPT to go read them and say, summarize all these things for me in this manner. I'm building this kind of model. I need to know the following sorts of things. Go ahead and do it, and they'll go do it. So I think that's where those are the sorts of things where AI can really assist us, but not do it for us. Even if it could do it for us, I don't think we want to have it do it for us.
Well, in the context of your simulators, could AI help find the leverage points that you were describing earlier, or be a pilot, so to speak, of the simulators and do like a massive number of I don't know what you call them, permutations, or like basically the decision tree of all the different ways they would navigate through that, or something like that?
Yeah, it's kind of like a Monte Carlo experiment or something. Yeah, great idea. I hadn't ever really thought about that, using AI in that manner. But again, that's something where that's reasonable, right? That sort of thing is like, okay, we've got an interesting flight simulator here, game. And instead of trying to get 1 million people to play it, great if we can. Why don't we have AI play it 1 million times or whatever and see what? Yeah, that's a good idea. So no one has done that as far as I know, but it's a great idea.
Awesome.
Get a
Well,
doctorate student working on it.
right. Yeah. Well, just one last question. I'm curious if you could give the audience advice for anyone who's thinking about working in system dynamics or thinking about developing an interest in system dynamics. Where should they start, and how should they navigate this field?
You're loaded with great questions. That's a good one. There is a national society, or really international society, called the System Dynamics Society, systemdynamics.org. And they're kind of the international clearinghouse for all things system dynamics. I believe they said that the most frequently asked question they receive is, how do I learn how to do this stuff? So I'm sure they have answers. And there's various private organizations, universities, whatever, who are producing how do you do it materials, online materials. There's also an organization called the Creative Learning Exchange. They're located in Acton, Massachusetts. It's like cleexchange.org or something. I don't have the URL right at my fingertips, but it's the Creative Learning Exchange if you Google it. And they have, it's sort of the international clearinghouse for K through 12 system dynamics for teachers, and primarily of high school and junior high and what have you. And they have a lot of how do you do it materials as well. And I believe I heard one time that the most common download of their materials is not like high school teachers, but it's corporate executives. So they go to the K through 12 site to get material on how do I do it? How do I learn how to do it? The software has gotten very, I happen to have one, very user-friendly these days. Here's how I started. This is just a bookmark. I saved these, but I started on punch cards doing this stuff years ago on a mainframe. And it was quite clunky and it took forever. You thought really hard before you ran a simulation, because it was so involved to run one simulation that you really didn't want to make any mistakes, Now the software is very user-friendly. There's free copies available of, limited versions of it, but to get you going. So it's like giving a toddler a machine gun, lots of people can now build really terrible models. So what you want to do, if you're really interested in seriously learning this stuff, is at least learn how to properly run someone else's model. That would be kind of your beginner's level. Like I say, you go to either of these organizations, the System Dynamics Society or the Creative Learning Exchange, there's enough materials to get you going. IC Systems produces a program called Stella, which is also kind of the K through 12. It's very user-friendly. There are other packages that are good as well, Vents and PowerSim and what have you, but Stella would be a good one to look at to begin with, to get you going. It's fairly user-friendly. But the idea as a beginner would be, let's open up and properly use someone else's model or game, and just understand how do you do simulation experiments that are not willy-nilly, where you can actually learn and whatever. And then you go from there, right? Then you say, okay, I want to build my own. I don't want to just drive a car that somebody else has built. I want to build my own car to my specs, right? And that gets a little more tricky, and that takes a little more learning. Usually it's universities. There are a few companies that have training. And then I think finally, if you want to be sort of at the expert level, in addition to just practice, like anything, first time you hit a golf ball, you're not going to be very good at it, most likely, right? You got to do something a lot to get good at it. Same thing with modeling. But we find at WPI in the lab that even a doctoral student that's taken a bunch of classes and is quite serious about the whole thing really needs mentorship to build models at the highest level, where an experienced modeler says, okay, show me your model. What are you trying to do over here? And they tell you, and they say, okay, let me make a suggestion as to how to do that better, right? Because we've been doing this for a while. You have techniques and chunks of code and whatever that work. And you see at some point then the light bulb goes on and people are off to the races building very good models. An expert model would be one where it's technically correct, but also you don't know exactly what's going to happen before you press the go button. If you always know, even if the model's technically correct, why do you need the model? Right. If I make this number bigger, it grows faster. Well, did you need a model to, yeah, it's technically correct. It's original, but it's when it's counterintuitive, when these feedback loops are doing weird things and you're like, I don't exactly know why it did that. I better run some diagnostics. I better run it again. Now you're learning. It's telling you something you didn't know. And to get to that level, you really, I think, need some coursework and some mentorship. But to get going is easy.
Yeah. Well, thank you so much for taking the time, Mike, and sharing insight and wisdom. I hope we can continue the conversation down the road.
Oh, I'm delighted that you had me here, and I'm happy to talk to you anytime you want about this stuff.
Awesome. Thank you.